Morning, guys. In the last class, we have been discussing Fresnel diffraction patterns, and we talked about Fresnel zones mainly, and zone plates. Now, let's look into the diffraction from a rectangular aperture. The reason why we choose rectangular aperture is to start with. Is that it's a general case of a slit and also a straight edge. Because rectangular aperture, if you extend the aperture width to infinity in one direction, it becomes a slit. And if you remove one of the plates that makes a slit, that becomes a straight edge. And therefore, we start with rectangular aperture. We will see Fresnel integrals and also a very interesting construction that's called a Cornu's spiral. Okay. Here we have the figure. This figure, it is a screen. You have a screen here. Then this is your screen, and you have an aperture which has certain dimensions. And you have a point Q. You take point Q in the aperture, which is at a distance of R from origin. And your source is at a distance R prime from Q, and at a straight distance of H prime. And here we have S as the distance from point Q to P, and H the straight distance of the point P from O. As usual, we are interested in computing the field at the point P. Since it's a rectangular aperture, we take Cartesian coordinates with the x-axis and y-axis. Okay. As you can see, the source is fairly close to the aperture, and therefore it's the near field patterns that we are interested in, and also the wavefront is going to be a sort of spherical wavefront from a point source. Okay. We have done the main groundwork in the last classes, that is the Fresnel-Kirchhoff formula. The amplitude of the electric field disturbance at the point P is given by this equation, where R and S has the usual meaning. Then this is your Cartesian direction cosines, and also dA is the area element of the aperture. All we had to do is to adapt this Fresnel-Kirchhoff formula to our situations, that is a spherical wavefront falling on a rectangular aperture, and we want to see the intensity pattern if you place a screen at this point here. And it is straightforward to see that R square is x square plus y square. And we have done this, the second assumption, R plus S can be computed by, okay, this is R square over 2L plus H prime, where L is this one. We have done that in the while we were doing with Fraunhofer diffraction. As in the case of Fraunhofer diffraction, we make two assumptions, that the obligity factor cos n, or the cosine of the angle between the unit vector and s minus cosine of the angle between the unit vector and r very slowly compared to e to the power I k s. That means this is slowly varying. Okay. Now, which means its dependence on the variables of integration is not great. It is can be considered constant. Now, the second assumption is the radial factor 1 over r s, r times s, very slowly compared to e to the power krs is a rapidly varying function, and therefore we can take this, consider this as slowly varying, and therefore we can take this out of the integral. If you do that, then the Fresnel formula becomes simpler, because all of them were all the above the constants are accumulated here as a constant c, and if you start integration from x1 to x2, these are the if you do that, x1 y1 is the coordinate for the rectangular aperture here, this is x2 y2 for this one, and then simply have to integrate over the whole thing, and this is what you are going to integrate, e to the power I k x square plus y square. And we can separate the variables like this, and these are the two integrals, and sometimes it's easier if you introduce these dimensionless quantities u and v. U, as we have done last time, it is proportional to x, and v is proportional to y. Then you substitute for dx, dy, and the limits u1 and u2, and this is what you would get. E to the power I pi u square over 2. Okay, just got rid of k to l and all these things. You're getting into a standard format, and since instead of c we have given a new name for the constant, that is u1, which is c times pi l over k, comes from this one, and therefore integrals can be evaluated in terms of integrals. Okay, the limits for integration is u1 to u2 there, and you can use this integral 0 to p integral as a standard integral, and then use it to evaluate up. Here we have p, used a small p sorry, as the variable, and it is just to generalize the whole thing. It can be either u or v. Let's say in the horizontal direction it is v, because it's sorry, in the horizontal x direction it is u, and in the y direction it is v. There's nothing special about it, it's just a variable. And then or it is the limit of integration. Then e to the power pi I pi omega square is cos pi omega square plus I sin pi omega square by 2, and which means you have the real part and the imaginary part. You do it like this. This is your real part, your imaginary part, and therefore we have two integrals. The real part is integral 0 to p cos pi omega square over 2 d omega or dw, whichever you like to call it. Sp equals 0 to p sine pi omega square over 2 d. And these are called Fresnel integrals. Okay. Remember, it starts from the Fresnel formula. We have made certain assumptions, or then straight away you got Fresnel integrals. Now we can plot Sp against Cp, and there we get something called Cornu spiral. If you plot Sp and Cp, this is what you are going to get. Okay. On the x-axis we have Cp, on the y-axis Sp, and for each Sp, what is Cp? Cp is integral minus 0 to p, integral 0 to p cos pi omega square over 2 d omega, and Sp integral 0 to p sine pi omega square over 2. These are the two Fresnel integrals, and we plotted them with Cp on the x-axis and Sp on the y-axis. You get a spiral like this one, and we call it Cornu spiral. Then what I have shown here in yellow are the values of Cp, values of U and V. Okay. You can actually make values of P, sorry, P. P means it is either U or V. This is values of P. P is either U or P. Okay, remember that. Then you can also make tables, like if you have a value of P, value P is 0, C0 is 0, S0 is 0, and so on, 0.2, 0.4, all these things. And if the limiting case, when you have P equal to infinity, you get 0.5. The value will be 0.5. That is what is shown here. Okay, it the value goes up and up and up. It goes up, then it spiral down, 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 and at this point, when you get to infinity, you get 0.5 as the limiting value. This is same for minus 0.5. Here you have minus 0.5, minus 0.5. Both Cp and Sp will have the same value. Okay, and that is interesting. With this tabulated value of Cp and Sp, we could find out or we can get the diffraction pattern, especially when there were no computers. Okay. Now, okay, this curve is an actual curve which I have computed using MATLAB. It is really straightforward to do that. This is your small program. I have taken it from this guy, but even otherwise it's a very straightforward integration. Then there are some features of uh, Cornu spiral. The straight line segment, okay, here you have a point P1 on the Cornu spiral, here you have point 2 P2 on this. The straight line segment P1 P2 gives the value of P1 value integral P1 to P2 e to the power pi omega square over 2. Here the length of P1 P2 will give you the magnitude and projection on both ends, like this part projection, not this one, it is this projection here will give you the real part, and this will give you the imaginary part of the whole thing. It is real part. Just to elaborate, this is what you will get for the real part. Okay. And therefore the length will give you the magnitude of the integral. Also we can say that dc square plus ds square is equal to dp square. And therefore the total arc length of Cornu spiral is equal to the difference between the limits, that is p2 minus 1, which is, as you know, it is proportional to the size of the aperture. So what was okay, it is it's either or u2 minus u1 or v2 minus v1. That, okay, which means the arc length is equal to the difference between the limits. p2 minus v1 in the x direction, it is u2 minus u1, that is x2 minus x1 times 2 over lambda L, and also for the y direction v2 minus v1 is y2 minus y1 times square root of 2 over lambda L. Now we are going to consider a limiting case. This is a limiting case. I use this as I use infinite aperture. Okay, there is no sense if you use an infinite aperture, and it is equivalent to no aperture. There is no aperture. The reason why I do this is to find out what will be the intensity or the intensity in the absence of any screens. That will give you a normalization constant. That's the only reason why we do this. Okay. In this case, therefore, the limiting case u1 u extends from minus infinity to infinity, and v extends from minus infinity to plus infinity, and therefore u1 equal to v1 equal to minus infinity, u2 equal to v2 equal to minus infinity. Then up, the disturbance at the point P, is u1, okay, and integral u1 to u2 e to the power u square and v1 to v2 e to the power I pi v square over 2 dv. This is we have seen just now. Nothing special about it, and you can substitute for the limits minus infinity to plus infinity, and we know that c at infinity is half, and that is the same for or s at infinity has the magnitude half and I. Okay, that is your imaginary part. Similarly, for C minus infinity, it is minus half, and C S minus infinity is minus half I. If you do this, or you can, since it is going to be symmetric, you can use minus infinity to infinity as twice 0 to infinity, or whichever way you do it, you get something like u is equal to 1 plus I all square. Is reasonably straightforward. This is half I, this is half I. At infinity, at 0 is going to be zeros, and therefore if you apply the limits, this is what you will get. And that is the unobstructed optical disturbance, or the intensity, or the square of this will give you the intensity at that point if there were no screens. And this will be u1 times the length of the line from P to minus infinity to infinity. Okay, from this point here to this point here, that is 1 plus I all square. Therefore, UP can be written as a general form UP. This is your intensity U1. That is CP plus ISP U1 to U2. Okay. Instead of minus infinity to infinity, you use the real limits and V1 to V2. Or in the normalized form, if you substitute for U1, that is U0 over 1 plus I all square times this one. Okay, now you got an expression which we can use or it can be adapted to the specific situation we are in. There are certain remarks that you should realize. This is the expression is not valid for very large value of u and v. Okay, and also most contributions to UP comes from the lower order Fresnel source, and therefore large values of U and V does not contribute a lot to the intensity pattern. Therefore, the formulation is still very much valid. Okay. What have we done here? We have used an infinite aperture to find out the normalization constant, and then we use that normalization constant to find a general expression from U1 to U2, okay, a finite aperture under Fresnel diffraction using Fresnel-Kirchhoff formula, or starting from Fresnel-Kirchhoff formula. Let's see how a slit will diffract light. A slit means, as I said, it can be considered as the limiting case of a rectangular aperture, and in this case it take the x component. X, it extends from minus infinity to infinity, and in the y direction it let's say it goes from v1 to v2, and therefore according to this formula here, what we can use is for one of them we give the limit to minus infinity to plus infinity, and therefore c infinity plus I s infinity minus c in minus infinity plus minus I sine infinity. That is c infinity is half, I again s infinity is half, c minus infinity is minus half, and this is minus half, and therefore this is what you will get. Half plus half is 1, half plus half is 1, and therefore this becomes 1 plus I, and 1 plus I and 1 plus one of them will cancel out, and therefore UP in this case is U0 over 1 plus I CP plus ISP. Let's see, now the limit is V1 to V2. Or when you say this limit, you may not be using such limits outside a bracket like this. But remember, this is an integral. It is the limit of that integral that we put here. Now look at a straight edge. Straight edge is the limiting case of a slit with, again, this was your slit minus infinity. U was from minus infinity to plus infinity. This was V1 to V2. Now okay, you can either put V2 equal to infinity by removing this part, or you can keep V1 at minus infinity. This is what I heard on here. V1 equal minus infinity, and V2 remains there, or the one of the plates that made a slit remains there. And in that case, how will it look like? Because this is your expression. In this case, UP will be U0 over 1 plus I. Then you take V1 as minus infinity. That means C V2 plus I S V2 minus I minus C minus infinity minus my S minus infinity. And this is minus half, minus minus half, that is half, and minus minus half I. Okay, there is an I here. That's what I have used here. Half plus half I, and this is CV2 plus I, okay, this thing here. And therefore, UP is a function of only one variable. Now, it is V2. V2 specifies the position of the diffraction edge. Now, what will be the intensity or U0 exactly at the shadow edge? Okay, this is your situation now. We have a spherical wave coming in. Now, this is your shadow edge. Ideally, if there were no diffraction, you should have had a perfect shadow, and this is V2 equal to 0. If V2 equal to 0, this is what you will get. U0 over 1 plus I, half plus half I, if you apply the limits. Because this CV2 becomes 0, and SV2 becomes 0, and therefore what remains is these terms here. Therefore that is what you see here, half plus half y, or the amplitude, field amplitude will be half of the original one, or by placing an efforts there you have reduced the intensity only by half. Ideally it should have been 0. This means that amplitude at the shadow edge is one half of the unperturbed value, and therefore the intensity is 1/4 of the unperturbed. Okay, intensity is up square, and therefore that is 1/4 of the. Let's see how. Let's plot it and see. Okay. As a function of V2. Okay, V2 is here is your aperture knife edge. V1 is somewhere here minus infinity. V2 is something that we vary. This is V2 equal to 0. Then this is V2, let's say, equal to 1, and so on. And at some point it is going to go to infinity. Okay, this is what you will see in this picture here. This is what I have plotted, UP, or I have plotted the intensity, UP, UP star. IP is UP star. Okay, I have written it here. See, at V2 equal to 0, this is what we get. By the way, that while computing that, there was a mistake in the actual values, I think, and therefore I had 4 at the background. It should have been 1. And this is a graph which shows the values with the correct scaling, but the overall behavior remains the same. Now this is at v equal to 0. Okay, this is plotted as a function of v2, or in other words, this is something that might be the intensity pattern, like this is what is here. This is okay, v equal to 0. There is that is I0 by 4, and here we have another intensity where it peaks. Then we have a minimum point, then you have a maximum point, and so on the shadow. That is on the illuminated region. Here, this is the illuminated region from 0 upwards, and this is the shadow region from 0 downwards. And this is how the intensity pattern will see. There will be, you may have seen it with the laser diffraction. There will be a series of peaks on the actual curve. Now let us see. Okay, here is a point where you have maximum density, and that point is when V2 is 1.25, and this value here is 1.37 times I by I0. Normalized intensity is 1.37 times, or the intensity is 1.37 times I0. It's higher than the actual, and at the end, after all this oscillation, it's going to settle down to the intensity, the original intensity, as V2 goes to infinity. Okay, and which means it's only near the near the knife edge or near the geometric shadow, we will be able to see the oscillations, intensity oscillations. And in the shadow region, which is V2 less than 0, intensity falls off rapidly as V tends to minus infinity. This one, it just goes to 0 very rapidly. And in the illuminated zone, intensity oscillates with the diminishing amplitude about the unbounded value as V2 goes to infinity. Highest irradiance is at V2 equals 1.25, the value of IP 1.37 times. You can see this is about, this value here is about 1.25 and this is about 1.37. Okay, this is, here you have 1.5 and somewhere above that, I mean above the middle point unbitted. And with that, maybe we can stop here. Okay, what have we done? We have done detailed analysis of diffraction, Fresnel diffraction or near field diffraction of light of spherical wavefront or any arbitrary wavefront. I think it's a spherical wavefront from a knife edge, diffraction from a knife edge. We have seen the how Cornu spiral can be useful in analyzing the diffraction pattern. Well, this is okay. Let's say if you were to do this using Cornu spiral, V1 is minus infinity. That is this point here. Now, for all these values, I have some corresponding values. This is 1. This is 1. Some corresponding values. It may not be exactly the same because 2. It is this point here. Then you have 3, which ideally should be 0, 0, and that is this thing. This point here, this is 4, where you have maximum. That is 1 point. It has to be 1.25 somewhere. Okay, 1.25. Okay, this is not okay. Here on the x and y axis, you have CV and SV. This is not the values of this is not what we are looking at. What we are looking at is the value here. These are the values for 1.25 is somewhere here. The value will be SP will be 0.65 and here we have roughly 0.62, something like that. Okay, and therefore it is need to understand this concept, then it's easier. Okay, you calculate CP and SP for different values. Let's take only one variable B. You calculate CV and SV, and if you plot that, you will get you can plot that you get some oscillating function, and here what is plotted for Cornu spiral is CV or CU and SV or SU, and all the points on this curve corresponding to particular values of U and V, and that is what we were interested here. The U and V are the actual real values, spatial values, which is proportional to x and y, and those values for each value of U and V. For example, let's say you can calculate values for, okay, if you want to plot. Now it wasn't easy to find the diffraction pattern like this when there were no computers, and the Cornu spiral method was very useful during that time because you can, for let's say, for V equals V2 equals 0, C0 is 0 equal to S0, and therefore UP can be calculated using this formula, and that will be at the point P, that is half plus half I, or that is uh, times U0 over 1 plus I, okay, this constant here, and what will you get? That is U0 over 2, that is half the amplitude or quarter of the intensity. Now, if you were to calculate the value, okay, you have to calculate. Uh, you get U C C P or and SP from standard tables, or somebody has calculated it for you to call the paint to calculate it. Then for you are interested in the intensity at this point, or at this point, let's say. Here we know that the V2 equals 1.25, and what we will be what we want to calculate there is UP is U0 over 1 plus I, C at 1.25 plus I, S at 1.25 plus half I. Now you look into the table. What is C 1.25? We had the table, or you can calculate, right? Okay, we have 1.2, and from my calculation, I think it is 0.68. Okay, C 1.25 is 0.68, and CS 1.25 is 0.65. It's some more decimal place. And then, okay, now we can use that value here. Okay, this is 0.68. This is 0.65. You know what half is, what half I is. You get something here divided by 1 plus I. Then you have to separate it into real and imaginary part. Therefore, that is some value plus I, some other value. Then IP will be this. Okay, let's say this is A, this is B, A square, അല്ലെങ്കിൽ A plus IB times A minus IB, or that is the intensity at that point. What you will see is that is, if you substitute all this value 1.37 1.37 square I0, that will be the value of the intensity. Oh, no, it's a 1.37 times I0. Okay, that is what it is here. This is the intensity, and this is, okay, not there. That is not the correct figure. This is the correct figure, 1.37 times that. And like that, if you do it for all these points, you can actually reconstruct this figure. And that is the use of Cornu spiral. Okay, thank you.